Hello AP Chemistry students, and welcome to section 2.2 on intramolecular force and potential energy. In this, we're going to be representing the relationship between potential energy and the distance between atoms based on the factors that influence the interaction strength. And if that sounds a lot like Coulomb's law stuff, that is because it is. So intramolecular forces are just a fancy way of saying bonds. The prefix intra means inside, so these are the forces within a molecule, the forces that are holding the atoms together to form the molecule. And they have a potential energy associated with them that's determined by the balance of forces holding them together. This is where we get into the Coulomb's law stuff, where we are thinking about the strength of the pull of the nucleus, and then the effect of the distance between the two atoms. And this idea applies to all bonds, covalent, ionic, or metallic. So let's look at the graph below, which is a distance versus potential energy graph. On our x-axis, we have internuclear distance in picometers, which are really, really small. And on the y-axis, we have potential energy in kilojoules per mole. And if we start on the right side of this graph, we can see that we have two hydrogen atoms at a distance of 300 picometers. And these two atoms aren't really having any interaction. And you'll see as a result, they have zero potential energy because these atoms have not gotten close enough to each other for their electrons to start to form bonds yet. But as we scoot to the left here, you can see the potential energy starts to decrease as the atoms get closer together until they get to a point where the atoms are starting to overlap. Their electron clouds are overlapping, and their valence electrons are transferring electrons between them and sharing those electrons to make a covalent bond in this case, since it's two nonmetals. But you'll see that this potential energy keeps getting lower and lower as they get closer. And a negative potential energy is associated with stability. And what I mean by stability is they're trying to find like a comfortable place. Like if you hold like a ball in your hand, it has some potential energy associated with it. But if you drop it, it's going to land on the ground and then kind of stabilize. And at that point, it's going to have a negative potential energy because you're going to have to put a bunch of energy into it to like pick it up to overcome that sort of stability. And in this case, you can see that around 74 picometers is when it reaches the minimum potential energy. So this is the most stable distance between these two atoms, which is represented here as R0. And this is an equilibrium point. This is where a balance has been achieved between all of the different factors, between the attraction from the electrons in one atom to the protons in the other, and then also a balance between the repulsion of the electrons in both atoms and the repulsion of the protons in both atoms. And speaking of the protons, you can see if they start to get closer, and we get up to here to 45 picometers, now we have a positive potential energy. We've become the opposite of stable. These two hydrogen atoms have gotten too close to each other, and now their nuclei are starting to repel each other. So this becomes very unstable. So for any bond, there's going to be sort of a perfect distance between the two atoms where they're most comfortable and their potential energy is the most negative it can be. So for covalent bonds, this length is determined by a couple factors. One is the bond order, which is like the number of pairs of electrons being shared. And in chemistry, we mainly see single, double, and triple bonds, as we can see here. And this causes a couple things. So on this table here, we have sort of a summary of the things happening in multiple bonds. Ignore this bond designation one for a sec. We're not going to talk about that until later in the class of sigma and pi bonds. You'll know what that means later. But for bond order, single bonds are considered to be a bond order of 1, double is 2, triple is 3. And the length associated with this, that with a single bond, that's the longest type of bond. And you can see that in this image here. And as we get 2 and then 3 bonds, this length sort of shortens. So you can think about it in terms of the strength of interaction between them. As a pair of electrons is being shared, there's going to be a stable attraction between these two atoms. If it shares another electron, they're going to get pulled, or another pair of electrons, they're going to get pulled tighter into each other, and that bond is actually going to get stronger as a result. You throw on a third bond on there as well, they get even closer and even stronger. So we see as the bond order increases, or the number of bonds increases between two atoms, the length decreases, they get closer to each other, and the strength increases. And that makes a lot of sense. If you think about, like, if you taped two things together, if you add more tape to it in more places, that interaction is going to be stronger and going to be harder to pull those two things apart, because you're going to need to overcome more of that adhesive force of the tape. So it's kind of the same thing here with the bonds. The more electron pairs being shared, the stronger and tighter the bond will be, and the more potential energy it contains. And what I mean by potential energy in this case is like how much energy you're going to need to put in to pull them apart, how much energy you're going to need to break those bonds. For ionic bonds, the length and strength of the bond is pretty simply explained by Coulomb's law stuff. So smaller atoms, which have a smaller distance to the nuclei, are going to have a stronger attraction to each other. And then also the larger the charge of the ions, like a 2 plus charge or a 2 minus charge versus a 1 plus charge or a 1 minus charge, is going to have a stronger interaction as well. And we see that in Coulomb's law, like the Q1 times Q2 on the top. The more those charges increase, the more the force between them increases. So if we're comparing like +1 and -1 type ions, the smaller the ions involved in that ionic bond, the more the attraction is going to increase. And then if we're looking at the types of charges, +1 and -1 versus +2 and -2, the attraction is going to increase as the charge increases. So let's do a little practice. So I made an ionic bond energy championship bracket. So we're going to compare a couple ionic bonds of a couple different substances, and we're going to try to decide who's going to be the strongest of all of these bonds between magnesium selenide, magnesium sulfide, potassium chloride, potassium iodide, cesium bromide, lithium fluoride, strontium oxide, and potassium fluoride. So let's look at the first brackets. So magnesium selenide versus magnesium sulfide. Well, both of these magnesiums are 2 plus. Selenide and sulfur are in the same column as oxygen, so they're going to have 2 minus charges. So 2 plus, 2 minus, 2 plus, 2 minus. So they both have the same charge. So the strength is going to be associated with the size in this case. Sulfur is a smaller atom than selenide, so we can assume that magnesium sulfide is going to win this championship. All right, let's look at the next one, or win this game. So for potassium chloride versus potassium iodide, similar situation. Potassium is +1, both chloride and iodide are -1, so they both have the same charge, so we're going to have to refer to size in this case. And chloride is smaller than iodide, so potassium chloride is going to win this one. So we're going to get magnesium sulfide and potassium chloride here. All right, the next section, cesium bromide versus lithium fluoride. +1, -1, +1, -1. So we're going to have to defer to size again. Cesium and bromine are pretty big atoms. Lithium and fluoride are pretty small atoms. So the size is going to win here. So lithium fluoride is going to move on. And then this last one, strontium oxide versus potassium fluoride. Here we have +2, -2 versus +1, -1. So even though strontium is kind of a bigger atom than potassium, and then oxygen and fluorine are similar in size, the charge is going to kind of beat the size in this case, and strontium oxide is going to move to the next bracket in this case. All right, so now we have magnesium sulfide versus potassium chloride. So magnesium and sulfur, 2 plus 2 minus, potassium chloride, +1 -1. So we have 2 plus and 2 minus charge versus +1 and -1 charge. In this case, since they're similar sizes, we're going to have to defer to the charge here. So I think magnesium sulfide is going to win this one because it's +2 and -2. For this next matchup, lithium fluoride versus strontium oxide, we have +1, -1 versus +2, -2. Similar situation. Even though the lithium fluoride is much smaller, the larger charges of these two atoms is going to win out in the end. So our final bracket is going to be magnesium sulfide versus strontium oxide. So this is going to be kind of tricky to consider since we have a +2 on both of our cations and a -2 on both of our anions. And let's see here. The cation is going to be really big. It seems like strontium is going to be a really big atom compared to magnesium. And then even though sulfur is a little bit bigger than oxygen, the size difference between sulfur and oxygen is not as great as the size difference between magnesium and strontium. So I think in this case, magnesium sulfide is going to be the final winner in our ionic bond energy championship. So hopefully that helped explain the intramolecular forces in ionic bonds and covalent bonds. And I'll see you in section 2.3.